Imagine, just for a moment, that everything you think you know about our place in the cosmos is not just incomplete, but perhaps fundamentally off base. What if the Milky Way galaxy, the island of stars we call home, is not located in some typical patch of the universe, but is instead floating in the center of an immense, almost unfathomable void, a cosmic bubble so vast it stretches nearly 2 billion light-years across? And what if this colossal emptiness isn't just a quirk of cosmic geography, but the missing puzzle piece behind one of the greatest mysteries facing modern science? Why do different methods of measuring the universe's expansion contradict each other so stubbornly, even after decades of painstaking effort? Welcome to the heart of the Hubble tension, a profound riddle that has become the defining challenge for cosmologists in the 21st century. Since the groundbreaking work of Edwin Hubble in the early 20th century, scientists have raced to pin down the Hubble constant, the essential number that describes how quickly galaxies are receding from each other as the cosmic fabric itself stretches. But here's the cosmic plot twist. If you use different tools and look at different epochs, you get two dramatically different answers, both backed by mountains of data. Let's break this down. If you turn your telescopes to the earliest light in the cosmos, the cosmic microwave background, a faint afterglow left over from the Big Bang, your calculations suggest the universe is expanding at about 67 kilometers per second per megaparsec. For reference, a megaparsec is roughly 3,260,000 light-years. That's an almost incomprehensible distance. A single megaparsec is enough to fit 25 Milky Way-sized galaxies in a line. But if you focus on the relatively nearby universe, measuring the brightness and distance of objects like Type Ia supernovae or Cepheid variable stars, you get a noticeably faster expansion rate, closer to 73 kilometers per second per megaparsec. That's a gap of about 10%, a gulf far too significant to chalk up to measurement error. Why does this matter? The Hubble constant is more than just a number. It's a cornerstone of cosmology. It tells us how old the universe is, how large it is, and even hints at how it might ultimately end. The fact that two of our most rigorous, time-tested methods give us incompatible results isn't just annoying. It's a potential sign that, somewhere, our understanding of the universe is missing a crucial piece. Some experts, like Nobel laureate Adam Rees from Johns Hopkins University, have put it plainly. It's pretty clear there is a very strong tension between the local estimates of the Hubble constant and the cosmic microwave background roots estimates. To try to solve this, scientists have proposed a dizzying array of explanations. Maybe something unexpected is happening with dark energy, the mysterious force believed to be accelerating the universe's expansion. Maybe there are subtle errors in our measurements. Perhaps Type Ia supernovae aren't the perfect standard candles we hoped. Or there's some hidden bias in the way we calibrate distances to distant galaxies. Or perhaps the laws of physics themselves need to be revised, with new particles or forces lurking just beyond our current models. Each possibility carries staggering implications for what we think we know about reality. Yet in recent years, a bold new idea has emerged: the local void hypothesis. To understand this, picture the universe not as a uniform sea of matter, but as a vast, three-dimensional cosmic web. In this web, matter is distributed in an intricate network of dense clusters and huge, nearly empty regions called voids. Galaxies, stars, and planets are like bright knots in this web, while the voids are stretches of space that contain far less matter than the cosmic average, sometimes less than 1/5 the usual density. Some astrophysicists, including Indraneel Banik from the University of Portsmouth, have become leading voices in this area. Banik explains, a local void slightly distorts the relation between the angular scale of baryon acoustic oscillations and redshift, potentially explaining the Hubble tension. In other words, if we live in a region of space that is about 20% less dense than average, and if that region stretches for almost 2 billion light-years, then the way gravity shapes the universe around us would be subtly different from elsewhere. Matter would be drawn outwards, towards the denser walls of the void, making our patch of the universe expand just a bit faster than the overall average. This could explain why local measurements yield a higher Hubble constant than those that average over much larger scales, like the cosmic microwave background. Imagine our galaxy as a boat, floating on a slowly expanding cosmic ocean. But the water is thinner around us than it is farther away. The currents would carry us outward faster than if the ocean were uniform everywhere. If this is true, it would mean our cosmic neighborhood is much more special, or at least more unusual than we've ever imagined. But not everyone is convinced, and the debate is anything but settled. The stakes are enormous. Daniel Skolnick, a cosmologist at Duke University, has described the Hubble tension as a crisis, suggesting it could mean our entire model of the universe is broken. Meanwhile, Wendy Friedman from the University of Chicago offers a more cautious optimism, stating that new evidence is suggesting that our standard model of the universe is holding up, although further measurements are needed. To test the void hypothesis, astronomers have turned to some of the most advanced techniques ever developed. One of the most powerful tools is the study of baryon acoustic oscillations, or BAO. To understand BAO, imagine the universe as a baby, just a few 100,000 years old, filled with a hot, dense plasma where matter and light were locked together. Gravity and radiation combined to create immense pressure waves, cosmic sound waves, that rippled through this primordial sea, much like the vibrations on a drumhead. As the universe expanded and cooled, these waves became fossilized, frozen into the large-scale structure of the cosmos. Today, their imprint appears as faint, concentric rings in the distribution of galaxies, each one about 1 billion light-years in diameter. By mapping these ripples, astronomers have created a sort of cosmic standard ruler. Since the size of these rings is known, they can be used to measure distances across the universe with stunning accuracy. If the local void hypothesis is correct, it should leave a subtle but measurable signature in the pattern of BAO. Specifically, the void would slightly distort the relationship between the angular size of these rings and their redshift, the amount by which light from distant galaxies has been stretched as the universe expands. Bannock and his colleagues have analyzed over 2 decades of BAO data, cross-checking results from different galaxy surveys, regions of the sky, and time periods. Their findings? The data seem to favor the void model by an astonishing margin, about 100 million times more likely than a model without a local void, according to their calculations. That is not a trivial difference. But science is rarely so simple. Other research teams, using alternative methods, have come to different conclusions. Some studies suggest that the void model cannot fully resolve the Hubble tension, and point instead to the possibility that the solution may lie in previously unknown physics, such as evolving dark energy, undiscovered particles, or even a need to revise Einstein's general relativity. David Spergel at Princeton University, for instance, notes that using the ACT data, we have tested many models and find no evidence for new physics or a higher Hubble constant. The debate continues, fueled by each new dataset and theoretical breakthrough. The search for answers has only intensified as new astronomical instruments come online. The Dark Energy Spectroscopic Instrument, or DESI, is currently mapping the positions of more than 35 million galaxies, creating the most detailed three-dimensional map of the universe ever constructed. By tracking how galaxies cluster and move over billions of years, DESI aims to reconstruct the universe's entire expansion history and provide the most precise tests yet of the void hypothesis and competing ideas. At the same time, the upcoming Roman Space Telescope, scheduled for launch in the middle of the 2020s, is set to revolutionize our ability to measure cosmic distances and trace the influence of dark energy. With its unprecedented sensitivity and wide field of view, the Roman telescope will peer farther into space and further back in time than any previous mission. Experts believe it could play a decisive role in finally settling the Hubble tension, either by confirming the void hypothesis or by pointing to even deeper mysteries. But why does any of this matter to us, sitting on a small blue planet in a quiet corner of the Milky Way? The answer lies in the very nature of scientific discovery. The Hubble tension is more than an abstract dispute among astronomers. It's a vivid example of how even the smallest inconsistencies can spark global debates, drive billions of dollars in research, and lead to technological breakthroughs with far-reaching effects. The tools developed to measure the distances to galaxies, everything from supernovae to Cepheid variables to BAO, have transformed not only astronomy, but also fields as varied as medicine, finance, logistics, and artificial intelligence. Consider this. Techniques and algorithms originally designed to sift through the enormous datasets produced by galaxy surveys are now at the heart of machine learning and big data analytics. Applications range from self-driving cars that interpret complex visual environments, to medical diagnostic tools that analyze images and genetic information, to logistics systems that optimize global supply chains. In a very real sense, our quest to solve cosmic mysteries has become an engine of innovation for society as a whole. There's a poetic side too. Baryon acoustic oscillations, the ghostly sound waves etched into the large-scale structure of the universe, are literally the echoes of the primordial cosmos. Every time astronomers map these ripples, they are hearing the faint music of the Big Bang, a melody that has been playing for more than 13 billion years, shaping the architecture of everything we see. It's a reminder that even the emptiest reaches of space are alive with ancient history. If the void hypothesis is confirmed, the implications would be profound. It would mean our cosmic address is far from average, that the laws and constants we derive from our vantage point might not be universal after all. Scientists would need to revisit and possibly rewrite the narrative of how the universe evolved, how galaxies formed, and even how life might arise elsewhere. The boundaries of cosmology would shift, possibly forcing us to consider new forms of matter or energy, or to rethink the very nature of gravity itself. Tamara Davis from the University of Queensland puts it succinctly. It's important to consider a range of possibilities, including both observational errors and new physics, to fully address the Hubble tension. But if the void model falls short, the puzzle only deepens. We may be compelled to search for even stranger solutions, such as time-varying dark energy, new types of particles that interact only through gravity, or modifications to Einstein's revered theory of general relativity. As Adam Rees has emphasized, the tension is not going away anytime soon. It is, in fact, a very strong tension, and the puzzle is as compelling as ever. Some experts, like David Spergel, urge caution. He notes that, using the ACT data, we have tested many models and find no evidence for new physics or a higher Hubble constant. Yet, as data continues to pour in from DESI, the Roman Space Telescope, and a host of ground-based observatories scattered across the globe, the race is on to gather the evidence that will finally tip the scales one way or another. Looking forward, the next decade promises to be an era of unprecedented discovery. With every new survey and every sharper measurement, we inch closer to an answer. Whether it ultimately confirms the void, points to revolutionary new physics, or reveals an even deeper stratum of cosmic mystery, the process itself is a testament to human curiosity and ingenuity. The willingness to challenge our own assumptions, to test beloved models against the harsh light of observation, and to let the universe surprise us again and again. For students, enthusiasts, and professionals alike, the Hubble tension is a living reminder of the beauty and drama of science. It shows that our quest for understanding is never finished, that every answer breeds new questions, and that the universe always has another secret, waiting just beyond the horizon. If you find yourself captivated by these cosmic puzzles, consider this your invitation to join the adventure. Whether you're analyzing data, building new instruments, or simply pondering our place in the cosmos, your curiosity is an essential part of the great, ongoing story of discovery. And who knows, the next breakthrough might come from an unexpected quarter, a new observation, a creative insight, or perhaps even a fresh mind inspired by videos just like this one. So as we stand on the brink of new revelations, one question remains at the forefront. Are we truly living inside a vast cosmic bubble? Or is the reality behind the universe's expansion even stranger than we can imagine? The answer is still unfolding, written in the clustering of galaxies and in the whispers of ancient light. One thing is certain, as we peer ever deeper into the cosmos, the surprises will keep coming, challenging and inspiring us all. If you want to stay at the cutting edge of these cosmic mysteries, make sure to subscribe and hit the bell icon below. We want to hear your thoughts. Could the universe be hiding its biggest secret right under our noses? Or is the real breakthrough just around the corner? Share your theories, your questions, and your insights in the comments. Until next time, keep looking up, and remember, the universe